Welcome to lecture 35 on chapter 4, that is applications of Fourier representations and signal reconstruction. To brief you about the previous session, we understood and studied about how to relate the Fourier transform to the Fourier series, and also we learnt about how to relate DTFS and DTFT, and we could solve some problems on it. So of course, it needs a lot of strong prerequisite of the Fourier representation, all four classes. Assuming that you people have remember and understood the all the kinds of Fourier representation, we have begun this chapter. And the another two relations that we are deriving in this session are Fourier transform related to DTFS and FT related to DTFT. So these two relations we'll take it today. So let me share my screen. In lecture 35, we are studying about relate FT and DTFT, relate FT and DTFS. If time permits, we'll also cover convolution and multiplication. So before we proceed, I had given you an assignment regarding the second kind of relation, that is FT to DTFT, DTFT to DTFS. The problem goes like this. So x of n is cos of 7 pi n by 16, wherein it is a periodic signal. You are supposed to apply DTFS to it, but I'm asking you to represent it in terms of DTFT coefficients. So that's why the very first job is you need to find its period. So n should be replaced with n plus capital N. So 7 pi capital N divided by 16 should be equated to 2 pi m. You will get n equal to 32 by 7 into m. So m, by selecting m value as 7, your n value will be 32 samples. Okay, with this we can find out the omega naught, which is fundamental period, 2 pi by n. So you get it as 2 pi by 32 pi by 16. Okay, so you know that by Euler's theory we can represent the trigonometric cost function as 1 by 2 into e raised to j 7 pi by 16 n plus 1 by 2 e raised to minus j 7 pi by 16 n. It is a Euler's formula you already are aware of. Why we use this thing is in order to find the solution by inspection method. So by inspection, what we can do is, I'll write the standard definition here. X of n is equal to summation x of k e raised to j k omega naught n. So here I to for making simplicity, so I just write it in much more easier way. So e raised to j k into the bracket pi by 16, because omega naught we have found out it to be pi by 16 into n. Now by comparing this equation with whatever the given question, you can see that in place of x of k I am having 1 by 2. In place of k, what I have to substitute? It's 7 here, and there is minus and 7, so it is minus 7 here. So hence for k plus or minus 7, I am having the constants coefficients as 1 by 2, and for the other values it is 0. So by this way we could find out its DTFS coefficient x of k. Now we need to stop. We should not stop here, because we are being asked to find out DTFT. So DTFT and DTFS relation goes like this, which we had derived in the previous class, earlier class. So 2 pi summation x of k delta omega minus k omega naught. Omega naught is already found out as pi by 16, and x of k exists only for minus 7 and plus 7. So we will write it. So k substituted with minus 7 will get you this much. K substituted with 7 will get you this much. Okay. So and the last one is so pi. So here is a pi 1 by 2. 1 by 2 here and 1 by 2 cancels. 2 cancels. So pi is left. Pi delta omega minus 7 pi. Here omega naught is replaced by pi by 16, so that's why pi by 16. Pi delta omega plus 7, so delta naught is nothing but omega naught is nothing but pi by 16. So this is the answer for your the assignment that has been asked in the previous class. Now to begin with today's class, the very first thing I had taken is relating the FT to the DTFT. So consider discrete time signal x of n and its DTFT. So the pair can be written as, the DTFT pair can be written as X of n is a time domain signal. Capital X of j omega is e raised to j omega is the frequency domain. Let me name it as 1. So x of e raised to j omega is written as summation n is equal to minus infinity till plus infinity x of n e raised to minus j omega n. This I call it as equation 2. This is a standard form, right? Standard definition it is. Now, let us consider FT pair now. Consider CTS, continuous time signal, FT pair. So FT pair, I denote it as, rather than writing it as x of t, I write it as x delta of t. The reason for writing this x delta I'll tell you later. FT pair can be written as x delta of t is a time domain signal, capital X delta of j omega is frequency domain signal. So this is equation 3. Now what we do is we try to relate equation 1 and 2, pair 1 and pair 2, pair not 2, 3 it is. We try to relate 1 and 3. So x delta of t is a complex sinusoid which can be represented as e raised to j omega t, whereas x of n is e raised to j omega n. Okay, so whatever signal representation we are doing in Fourier, what Fourier says is any signal can be represented using complex sinusoid. So if it was continuous time or Fourier transforms, its input is given in this fashion. If it is discrete time, it is given in this fashion. Now we want to try to relate it, because in real time we have a continuous time signal, but our hardware, our processor, our program, everything can be worked only on discrete time signals. So hence I need to derive the relation between these two things. Okay, to be more precise, x delta of t is nothing but it's a sampled signal from the original x of t. Sampled means there is a continuous signal like this, something like this. Sampled signal is I extract this particular information, this particular information, this particular information, this information. After every certain time, I extract the information and I build the signal like this. I have this information, I have this information. So it's same information, but I don't store all the values at each time interval. So I take the samples at every ts amount of time. First ts amount of time, I extract this sample. Next ts amount of time, I extract this sample. Next ts amount of time, I extract this sample. So this is called sampling, right? You're aware of it. From sampling, your continuous time signal becomes a discrete time signal, or else in the equation wise I can tell it as x of n is equal to x delta of t. So it is a discrete time signal. So after sampling I get a discrete time signal. It is nothing but x delta of t. It is nothing but samples received from the continuous time signal. So here t is NTS. Why it is NTS? Because at 0 TS, I extract that sample at 0th time. At 1 TS, I extracted here. At 2 TS, I extracted here. At 3 TS, I extracted here. So hence, at every TS amount of time varied with increasing integers, I go on extracting the sample. Hence, I represent this equation in this manner. So hence, to just proceed with what we had earlier written, x of n is equal to x of n is equal to e raised to j omega x delta of t. I could have written x delta of t is nothing but e raised to j omega n ts here. I should have placed bracket here. Let it be j omega as it is n ts, because in place of t I'm writing n ts according to this equation. So it is nothing but x delta of t. It is nothing but x of n itself. Okay, so x of n is equal to, see, minor changes I make, e raised to j. Now I take this ts with omega and I write n in this way. Now I compare this one and this one you just here. If I compare these two things, I get that omega in place of omega, jn is there. In place of omega, I'm having small omega ts. So this is the important concept that I need to use now. So with this, what I conclude is if x delta of t and x of n can be related, then similarly capital X of delta j omega can be related with capital X of e raised to j omega. This is discrete times Fourier transform by a small change, that is substituting capital omega with small omega ts. This suffices the need. This is what I wanted to derive. Okay, so now from 2, from equation 2, where is equation 2? This is equation 2. In place of equation 2, I write everything same. So in place of that, what I do is I write x of j omega. I remove this, I write x of j omega. I make only one change. What is that change? Wherever you have omega, capital omega, replace it with small omega ts. Wherever you have omega, replace it with small omega ts. That is what I'm doing. From 2, capital X of delta j omega is equal to this itself. So from 2, I write the equation the same manner by substituting omega is equal to small omega ts. That's it. X of n e raised to minus j omega ts n. That's it. That's it. Okay. This is an important derivation. Now taking its inverse Fourier transform, what we get is, see, capital X delta of j omega, if I take its inverse ft, I get it as small x delta of t. This is frequency domain, this is time domain because it is inverse ft. Now similarly, if I just give this kind of the signal, if I add this amount of this term into the frequency domain, so you know that we have studied from frequency and time shift property that whenever there is an exponential signal added or multiplied in the frequency domain, in the other domain, in the time domain, it will gives rise to a time shift. Okay, so in time domain, if you add a component, if you multiply a component of exponential, it will frequency shift. But in frequency domain, I'm having this. Hence, I need to have a time domain shift. So in time domain, the shift happens like this: delta t minus nts, because it is a time domain shifting. So nts. So that is what is a shift happening. Okay, so this is a ft, inverse ft of the exponential sinusoid, complex sinusoid. So therefore I can write x delta of t is equal to, by taking its inverse transform, summation n is equal to minus infinity till infinity, summation minus infinity x of n, same thing. So this is taken inverse, and this particular term, if I take its inverse, I get it as, so this to this, delta t minus capital small n capital ts. So this is again one more important derivation. So hence the final equation is, I have written here. So I'll write it here. X, this one I write first, and then I write this one. X delta of t is equal to summation n is equal to minus infinity till infinity x of n delta of t minus n ts. If you write ft pair of it, you will get this one, capital X delta of j omega. This is equal to summation n is equal to minus infinity till infinity x of n. So write this one, e raised to minus j omega ts n. That's it. That is the same equation I'm having here. Same equation. So this is the ft and dtft relation. So you should be very careful in deriving all these things, because you need to have a prerequisite. That's very important. Graphical representation here. Let me take x of n, some random value like this. Its dtft will result in this way. Okay, I'm having the frequency coefficients arranged in this way. Now, if I want to convert it into the x delta of t. It means it is a sampled waveform, So there is some waveform like this, some continuous waveform. I have taken a sample to which is resembling it. We call it as impulse conversion because convolution does it. So shifted impulses, you can represent any signal with shifted impulses. Now, if I take its ft, you can see that only changes minus 2 pi by ts because we have done omega is equal to small omega ts, or else this omega is equal to, I can write capital omega divided by ts. Capital omega components are here. You have to just divide it by ts. Capital omega component is minus 2 pi here. So divide by ts. 2 pi divide by ts. So that's the only change you need to make in the ft. So this is the relation between ft to dtft. Okay, the concept looks bit complicated at initial stage, but if you go through it once or twice, it'll be easy for you. Example here. So x of n is equal to a raised to n u of n. DTFT pair has been given. So this is the equation, time domain signal. This is frequency domain signal. So this is given actually. Now what we need to do is, this has been derived using some example of third chapter, so that we have already done. We have done it, assuming a less than 1. So now what we have been asked is you need to find the equivalent FT pair for it. So for equivalent FT pair, what we do is we have to, FT is applied for continuous time signal, right? So continuous time signal and discrete time signal is related with the previous analogy or previous concept that we studied. So x delta of t was equated to x of n, right? How it was equated? It is like the continuous time sampled at every ts, nts. At every ts time amount of time, the samples are taken. Summation n is equal to 0 till infinity, a raised to n is the given signal. So this summation means what happens is at one time, at n equal to 0, it is delta of t. So delta of t is non-zero only at t equal to 0. So at origin, whatever a raised to n value is there, that component is extracted. Hope you're understanding what I'm saying. Now when n is equal to 1, you have ts. So what value of t will make this delta of t minus ts 0? So t should be substituted with ts. So that at ts, whatever a raised to n value is there, that component will be extracted. So when I sum it up, all those things, you will get a continuous time signal, sampled signal, which will resemble the given x of n signal. So it is a very important equation for your understanding. If you have not understanding this, then you have problem in understanding the convolution sum and convolution integral, second chapter beginning. Still, I'm giving you the flexibility to ask the question. Okay, so please ask the question whenever you have doubt. So this is a continuous time signal. Now I am deriving the FT pair. So FT pair and DTFT and FT are related by replacing capital omega with small omega ts. That is what we are doing now. So this is the equation of time domain signal. In frequency domain, what we have to do is 1 by 1 minus a into e raised to minus j omega is given. Just replace this omega, capital omega, with small omega ts. That is what we have learnt in the previous relation. Omega is equal to omega ts. So that's it, your problem. The next problem being, sketch the representation x delta, capital X delta j omega of discrete time signal, x of n, some x of n signal is given here. For that, what you are supposed to do is you need to sketch the waveform. So here, let me tell you that I had solved you earlier. So this is resembling sinc function. You know that whenever the rectangular pulse is transformed, Fourier transformed, it will result in sinc function. And similarly vice versa. Whenever your input is sinc function, your output will be the rectangular pulse. So from previous chapter uh, studies of Fourier transform and DTFT, I'm writing this. If your x of n is sinc function like this, sine wn, not writing sinc, I'm just writing previous step of it because it is given in sine by pi n. So this was the derived and solved answer or question in the chapter 3. Okay, you can refer that. So if I take its DTFT pair, so it will result in rectangular pulse. Rectangular pulse can be written as 1 for omega less than or equal to W. This W, 0 in the range W till pi. So this is a given signal. Solved example it is. Now here what is given? Here sine 3 pi n by 8 divided by pi n dtft x e raised to j omega. So here I'm just making some change. In place of w, I'm having 3 pi by 8. So 1 for omega less than or equal to, in place of w, I'm having 3 pi by 8. Okay. So for 0 otherwise, you have to write it as 3 pi by 8 less than pi. That's it. Now very simple. So what they have asked is, assuming that Ts value is 1 by 2, what sketch the waveform. So you need to sketch the square waveform. That's it. Rectangular pulse you need to sketch, assuming Ts to be 1 by 2. Now here in this relation ft to dtft relation, we have learned that capital omega is small omega ts. This is what we have learned. It means small omega is nothing but capital omega by ts. So what is the first question given? Question A is ts is equal to 1 by 2. Therefore omega is equal to capital omega divided by 1 by 2, or else omega into 2. So what is omega? Omega is here 3 pi by 8. Within that range it should be 1. So 3 pi by 8 into 2. This is equal to 3 pi by 4. So rectangular pulse should be drawn such that it should stay 1 for omega less than or equal to 3 pi by 4, on negative side as well as positive side. So let me draw that. So here it is. From minus 3 pi by 4 to plus 3 by 4, it is 1, staying at 1. Rest everywhere it is 0. Correct? So similarly, the next question was Ts equal to 3 by 2. Ts equal to 3 by 2. So small omega is equal to capital omega divided by Ts. So this capital omega is 3 pi by 8 into 1 by Ts means I reciprocate this 2 by 3. 3 and 3 cancels. 2 ones are 2 fours are. This is equal to pi by 4. So minus pi by 4 to plus pi by 4, you draw the what is that? The rectangular pulse to be amplitude to be 1. So very simple problems. You need to just apply the things what you have learnt. That's it. So relating FT to DTFS. The again I just write it in order to make it simple for you. So very first step, what I do is I use two things here. So I use two things which we have already done. I relate DTFT to DTFS. This is already done, second derivation. And one more relation I use, DFT to DTFT. See, I am supposed to do FT to DTFS relation. Second relation we have done this one. This is a third relation. Okay. Second and third I utilize here in order to derive this. DTFT to DTFS, FT to DTFT to relate these two things. Okay. So first thing, step one, relate DTFT to DTFS. Capital X e raised to j omega is equal to 2 pi summation k is equal to minus infinity till plus infinity capital X of k delta of omega minus k omega naught. So next step is, this is a relation that I have taken from relation 2, derivation 2 that we did in previous session. Now step 2, this is first step, the second step. Relate ft to dtft that we just now did. X capital X delta j omega is equal to capital X e raised to j omega. So in place of capital omega, you need to substitute small omega ts. Okay, and also we had written capital X e raised to j omega. Now these two things I utilize to do it. So first equation I take 2 pi as it is, summation k is equal to minus infinity till infinity, x of k, I write it as x of k. Okay, so here delta of in place of capital omega, what I'm supposed to do? I'm supposed to replace small omega ts minus k omega naught. Don't replace omega. Omega naught is a constant. It's a fundamental period. Don't replace it with omega ts. Okay. Next, I make small changes here. Just here, 2 pi summation k is equal to minus infinity till plus infinity. Capital X of k delta. I'll take this ts common. If I take this common, what is left here? Omega minus k omega naught, but there is no ts exist here to take common, so hence I divide it by ts. So if you just cross check, so ts omega minus ts cancels k omega naught, so it will retain as it is, it will not disturb it. Okay, now I want to bring in front of you one concept that we had earlier studied. I'll write it here. We know that delta of a t, delta is an impulse function, at is 1 by a delta of t. So this we had studied in scaling property. I hope you remember. We apply this here. This is a delta function. Ts is a scaling factor. So using that property, this ts, I take it outside and write it as 1 by ts. So that therefore capital X of e raised to j omega is equal to 2 pi by this one a has been taken out and placed here. So ts has been taken out and placed here. Summation k is equal to minus infinity to plus infinity capital X of k. So whatever is left, write it. Delta omega minus k omega naught divided by ts. So this is your equation for relation between DTFT and DTFS. DTFS and FT. So this is DTFS. One second. Yeah, this is DTFS, and this is uh, actually I should have written it as, one second, I should have written it as, see, so I have substituted x delta of j omega is equal to a capital X of e raised to j omega. I have substituted it already. In place of omega equal to small omega ts, I have substituted. Means this one I should have written it as j omega, delta j omega. So this is ft coefficient, this is DTFS coefficient. So these two are the coefficients. So in order to write the relation, so I write it as, so if this is the time domain signal, n is equal to minus infinity plus infinity x of n delta of t minus n ts. Now if I apply ft to it, so I write the copy down the same equation that I had just derived just now. 2 pi by ts summation k is equal to minus infinity to plus infinity, x of k is DTFS coefficient, delta omega minus k omega naught by ts. So this is a relation between ft to DTFS. Okay. So now the diagrammatical explanation. If any signal is given like this, periodic signal, we apply DTFS with a fundamental period omega naught. We were getting the frequency components in this fashion as x of k. Now, if x of n is impulse converted to means assuming that it's a continuous time signal and sample is extracted at every ts, that you should remember, 1 ts, 2 ts, 3 ts, n ts, like that. Then if you take its ft, you will get it as the same components with that conversion that we have made. this one. Now we will take one example. The cos signal is there. So cos of 2 pi pi n is a periodic signal. It's a periodic signal and DTS signal. Actually, we need to apply DTFS to it. So to apply DTFS, it's very easy. 1 by 2 e raised to minus or plus j 2 pi by n, this n, plus 1 by 2 e raised to minus j 2 pi by n here. So we can write it here by inspection method. By inspection, we can as well write x of k as 1 by 2 for k is equal to plus or minus 1 and 0 otherwise. So we can write all those things. Okay, so now what we are supposed to do is we have to take the recently derived equation. So the equation goes like this: x delta of j omega is equal to 2 pi by ts summation k is equal to minus infinity till infinity capital X of k delta of omega minus k omega naught divided by ts. This is a standard equation. Now in place of x of k, what I'm doing is I substitute 1 by 2. I substitute 1 by 2. So 1 by 2 and this 2 cancels. Pi by ts is remaining. Pi by ts is remaining. Then here you just listen here. Omega in k, when I substitute it as minus 1, minus 2 minus plus, it becomes plus omega naught by ts. What is omega naught? Omega naught is nothing but 2 pi by n. 2 pi by n ts. 2 pi by n ts. It is nothing but omega naught by ts. That's the meaning. Both meaning is same. This we get when k is substituted equal to minus 1. When k is substituted equal to plus 1, you will get omega minus omega naught by ts. Omega naught by ts is nothing but 2 pi by n ts. Now why this is written minus m 2 pi by ts? Why this is written? Because the frequency part, the frequency domain signal will be periodic. It will repeat after every 2 pi by ts. That's why this component and this component you are supposed to write. So we had learned the four relationship in the previous two sessions. Relate ft to dtft. First we studied about relate ft to fs, then dtft to dtfs, then ft to DTFS, then FT to DTFT. So four relationship we studied, keeping in the mind that every signal should be able to be represented by FT. Now we could understand that any given signal to me, if I have been asked to represent it with respect to FT, it is possible for me by these four derivations. Convolution of periodic and non-periodic signal. So convolution of periodic and non-periodic signal, you know that. So in time domain signal, if the convolution operation we are doing, in frequency domain, we are just multiplying it. This we have studied in Fourier transforms properties, multiplication property and convolution property. Convolution in the time domain becomes multiplication in the frequency domain. And similarly, multiplication in the time domain becomes convolution in the frequency domain. The same concept we are utilizing. So convolution in the time domain results in multiplication in the frequency domain, one of the most advantageous factor of Fourier representation. So here x of t is a periodic by using its ft representation. Let us consider x of t to be periodic first. Recall from previous equations that ft of the periodic signal x of t, this is by relation 1, relation of ft to fs. This is this relation. We can represent periodic x of t. Actually, you should use fs, but we can use ft as well by using this relation. Capital X of j omega is equal to 2 pi summation x of k delta of omega minus k omega naught. Okay. Now, where x of k is a fs coefficients. This is fs coefficient. This is ft. We substitute this representation into the convolution property to obtain. So convolution property y of t is convolution of x of t and h of t. So capital Y of j omega is equal to multiplication of these two things. X of j omega is here, 2 pi summation x of k delta of omega minus k omega not. So you just multiply with impulse function, impulse response h of j omega. So now we use shifting property of the impulse to write. So shifting property of impulse, this is a shifted version, right? So we write it as, so 2 pi summation k equal to minus infinity to plus infinity h of k omega, we omega naught we write it here. So why we are doing it is because this delta function will be non-zero. I can say this delta function will be non-zero only when omega is substituted with, what? It is substituted with k omega naught. In rest all of the case, this delta function will result in zero, so everything goes zero. So hence I am interested in only this value, that is omega is equal to k omega naught. So this value I substitute in omega here and I take it here. So that's why h of j omega, in place of omega I am writing k omega naught, this x of k as it is, delta of omega minus k omega naught. So this is the convolution of the periodic signal, convolution of periodic signal. Okay, so the diagrammatical representation goes like this. Think that x of j omega is in this fashion. We get the ft coefficients of x of j omega is this, and h of j omega is the impulse response, system response given like this. If you multiply in the frequency domain, it looks in this fashion. See, as here it is going on to zero, so the frequency components are further suppressed. At in between, it is highly, as it is maintained or multiplied to the higher value. But as you go on increasing the frequency, this is a frequency, as the frequency grows, grows, your frequency components when it is multiplied at the input, so this will be suppressed. Okay, I can just quote this example as a low pass filter because it is passing low frequency components. This is a low frequency component, right? This is low frequency, these are higher frequencies, so it is passing low frequency components efficiently. High frequency component, it is getting, suppressed or attenuated. So with this we shall conclude today's session. So thank you.